Multiplexing and spreading, we are going to see today bandwidth utilization. Why we require bandwidth utilization? Because bandwidth is limited. Bandwidth has to be used wisely. So bandwidth utilization is the wise use of available bandwidth to achieve specific goals. Then the next part will say efficiency, which can be achieved by multiplexing, and also the privacy and anti-jamming that can be achieved by spreading. Bandwidth utilization is necessary because, just for example, FM. Now, for example, 200 kilohertz is given to one channel, the difference between two channels, so it is provided only 200 kilohertz for one channel, say 102.1, the national channel of that is called Rainbow India, 102.1. Then what about next one? Can it be 102.2 or can it be 102.0? Is it possible? We have specific frequencies that can be assigned. We need to utilize it the way it should be best in an efficient manner. Let me give you one more example. Thousands of companies, okay? Thousands of companies, multinational companies, international companies, or national companies. Telecom companies, there are so many. So they are assigned certain frequencies, certain bandwidths. Now they have limited frequencies. They have to make use of this only limited frequency to cater hundreds and thousands of the customers. How to do it? What is the way? We'll look at it today. This is multiplexing. Whenever the bandwidth of a medium linking two devices is greater than the bandwidth needs of the devices. What it means? That you have a bandwidth. They are users. You have a limited bandwidth. Now, what to do? They are users. They require more bandwidth. To cater to these users, you require a bandwidth which is not given to you or which is not possible even. So, you need to share the link. Two devices needs to share the link. What is the way? Multiplexing is the way. These are the set of techniques that allows the simultaneous transmission of multiple, not one, but multiple signals across a single data link. A data, or as data and communication uses increases, so does the traffic, and you have to manage the traffic with multiplexing. So we'll see all these type of multiplexing, namely FDM, that is frequency division multiplexing, wavelength division multiplexing, synchronous time division multiplexing, and statistical time division multiplexing. Again, we will revisit the multiplexing. These are the set of techniques that allows the simultaneous transmission of, this is the bandwidth, or this is channel. Transmission of multiple signals, not one, multiple signals across a single data link. Multiplexing. For that, we will use multiplexers at one side. Other side, that is RX side, will use or employ a demultiplexer. Then the path from RX to TX, this is a physical path. And the channel, the most important is the channel. The portion of a link that carries a transmission between a given pair of lines. So one line can have many channels. We'll see about it. When this word has come up, channel, let me give you one more example. You have a remote in your hand. Now, you press a key or a button, channel 231 comes up, your favorite channel. Then you press some other channel, 261, your kid's favorite channel. One more channel you press, 206 say, your wife's favorite channel. How can a single link, which is coming to your television from any way, I am not specifying whether you are using some cable or some satellite dish antenna, I'm not worried about this. What I'm worried about is, and what I want to explain to you, how can you see just by one wire, there is only one wire, 02999 in some services. this much of channels. How can you see? This channel is at certain different frequency. This channel is at a different frequency, or say time, or say wavelength also. We'll see about these three type of multiplexing. How can you divide a link into channels? This is only one link, but you have different channels. Say this channel, second channel, third channel, fourth channel, and input lines. And by multiplexing and demultiplexing, you can get n input and output similar n values. So multiplexing can be of three types: FDM, frequency division multiplexing; wavelength division multiplexing, that is WDM; and time division multiplexing. Now, you need to know that FDM and WDM are for analog signals. They are not for digital. TDM for digital. These are categories of multiplexing. Start with FDM. It's an analog technique. Analog. It has certain guard bands. We'll see about it. Why we need guard band. Okay. This is a teacher. Student 1, student 2, student 3. Now student 1 is talking, student 2 is talking simultaneously. This teacher can understand. He can't understand. Let them give some space or time. Let S1 speaks, then S2 speaks. Or let us allow them to talk in a different room. S1 talk to T, S2 talk to T. Right? Teacher can understand. There has to be some guarding, a brick, a wall, or a time gap. So we'll have a guard band to prevent signals from overlapping. How do we multiplex? The multiplexing process is that similar signal modulates different carrier frequencies. F1, F2, F3. So you have input lines, they are channels. F1, F2, F3. Who does this F1, F2, F3 in a single channel? How can you divide channel with respect to your frequencies? This is done by a multiplexer. And how can you combine these? How can you combine this? Or how can you find out this combined? Now this is frequency 1, this is frequency 2, this is frequency 3. You have demultiplexer here. FDM is an analog multiplexing technique that combines analog signals. Now, we go to the detail now. You have a particular signal, the other signal, one more signal. These are baseband analog signal. Let us modulate this signal with a carrier frequency F1. The result will be a frequency or a waveform like this. You have another signal, just modulate it with some other frequency. Any other signals? Say I have hundreds of signals. Don't worry about that. Modulate it with a particular frequencies. This F1, this F2, F3, they are different. These frequencies are different. We try to combine them. And we send only one signal after multiplexing them. This is what multiplexing means. What about the other end? Who is going to receive? What he is going to receive? And how he is going to receive? We have just one channel, one signal. But this is a multiplex signal. Multiplexed signal. So, there is a filter, or we can call it as band pass filter. Now, for every frequency, there is a filter. So it will, this first one go here, second one here, third one go here. Only this will be filtered. And this demodulator, what it does, it will take out that frequency and just try to pass the signal which was taken or which was sent in the receiver, or the sender part. This is taken by the receiver. This was sent by the sender, received by the receiver as it is. So these are baseband analog signals which are sent through the transmitter and received at the receiver using multiplexing, demultiplexing. Example. Assume that a voice channel occupies a bandwidth of 4 kHz. We need to combine 3 voice channels into a link. We have seen 3 voice channels just now, or any other channel, with a bandwidth of 12 kHz from 20 to 32. What will be the configuration using the frequency domain? Assume there are no guard bands. So what we are trying to do here is from 20 to 32. This is your bandwidth. What is the bandwidth? 12 kHz. And what 3 channels you want to send. A voice channel you want to send. 3 channels. 3 voice of 4 kilohertz. So there is a good criteria. 20 to 24, send first one. 24 to 28, send second one. 28 to 32, second third one. So we shift or modulate each of the 3 voice signals or channels to a different bandwidth. We'll see in this figure. But before going to the figure, let us understand that we use 20 to 24 kilohertz bandwidth for the first channel, 24 to 28 bandwidth for the second channel, 28 to 32 kilohertz bandwidth for the third channel. So these in all will cover from 20 to 32, and there is 4 plus 4 plus 4, that will be 12 kilohertz voice channel can be utilized here. How it actually works. These are 3 telephones, say. Voice means you want to call, and this guy wants to call this person. How can he call? And now when the other person would call, he would like to call him. How is he going to do? He has 4 kilohertz voice channel. All has. Modulator, it will carry these signals in the frequency range 20 to 24. This one from 24 to 28. This one from 28 to 32. Combine them. First frequency, second frequency, third frequency band. So you need n frequency band of n frequency channel for sending these 3 different voice channels. So you need a higher bandwidth link. Now it reaches here. We already have the bandpass filter. They will be filtered according to their frequencies, and this will be sent to 20 to 24, will send to this, and likewise. 5 channels each with a 100 kilohertz bandwidth are to be multiplexed together. 5 channels are there. What is the minimum bandwidth of the link if there is a need for a guard band for 10 kilohertz between the channel to prevent interference? So now we have 5 channels, and as we have known, for 5 channels each has 100 kilohertz bandwidth. 100 kilohertz bandwidth. So 5 channels, 100 kilohertz bandwidth. How much will it be? 500 kilohertz. So 500 kilohertz will be required. That is for sure. But we have to speak the minimum bandwidth concerning that guard band is also there. That is 10 kilohertz. So for 5 signals, 1, 2, 3, 4, 5 channels. This will be the first band, guard band, second, third, fourth. So 1 channel, 2 channel, 3 channel, 4 channel, 5 channel. 1, 2, 3, 4. 4 minimum guard band will be required. 10 kilohertz each guard band will take. So how much it will be? 10 into 4, that is 40. We add it here, so minimum will be 540. Let me tell you in a more formal way. We have 5 channels. We need at least 4 guard bands. This means that the required bandwidth is at least 5 into 100 plus 4 into 10, that is 540 kilohertz. Like this. These are guard bands. 4 guard bands, 10, that is 40. 4 channels, 500, 540. 4 data channels. Now this is a digital one. Each transmitting at a 1 Mbps. Use a satellite channel of 1 MHz. Design an appropriate configuration using FDM. How are you going to solve it? 4 data channels, 1 Mbps. 1 Mbps by 4, that is 0.25 Mbps. That is 250 kilohertz. So a satellite channel is analog. We divide it into 4 channels, each having 250 kilohertz. So each digital signal or channel of 1 Mbps is modulated with that each 4 bits is modulated to 1 Hertz. 4 bits modulated to 1 Hertz. So what would be our solution? We have already seen it previously. We can use 16 QM. How you can use 16 QM? Because 2 to the 4 power 4 is what? 16. So we use 16 QM, quadrature modulation. This is the more formal way of understanding. These are 250 kilohertz, that is 1 megahertz channel. We divide it into 4 parts, and this is 1 Mbps digital. And now we want to send 4 bits 16 QM, 16 QM, 16 QM. So we get 1 megahertz. This is analog hierarchy. How it works? These are 4 kilohertz 12 channel, that is 48 kilohertz. How many are these? 12 voice channels. We have 5 groups. These are 5 groups. So 12 channels, 5 groups, 60 voice channels. 48 into this much 5, that will be 240 kilohertz. Now 240, 10 subgroups of 60 voice channels. So 60 into 10, 600. Again 6 master groups, 600 into 6, 3600 voice channels. And the megahertz increases 48 kilohertz to we require the bandwidth of 16.984 megahertz jumbo group. AMPS, Advanced Mobile Phone Systems, it uses 2 bands. The first band 824 to 849, that is around 25 megahertz, is used for sending, and this for receiving 869 to 894 for receiving, sending and receiving. So each user has a bandwidth of 30 kilohertz in each direction. How many people can use their cell phone simultaneously? 25 kilohertz only, megahertz. 30 kilohertz, that is divided by 30 kilohertz. How many? Something around 833.33. Each band is 25 megahertz. You take a difference of 849 or 824, or rather 894 to 869, that will be 25 megahertz. We divide 25 megahertz by 30 kilohertz because each user would require a bandwidth of 30 kilohertz. We get 833.33, but in reality the band is divided into 832 channels. Why? Because 42 channels are used for control, so 790 channels are available for cell or cellular phone users. Now we come to WDM, Wavelength Division Multiplexing. How we can get it? Light. What is the basic characteristic of a light? How you can say 0.4 to 0.7 is the visible range? What is 0.4 to 0.7? Is it micrometer? What is this micrometer? This is a wavelength. This is a wavelength. So for light which is passing in fiber optics, we take lambda 1, lambda 2, lambda 3, combine them and then send them, and we know that light passes through prism. You can get Vibgyor. When you combine them, send through again a prism, they will send only one light, white light. This is the basis. So WDM is an analog multiplexing technique to combine optical signals. We have prism, as I suggested, combine them to lambda 1, lambda 2, lambda 3, that is fiber optic channel, a cable. Demultiplexing into lambda 1, lambda 2, lambda 3. So we have prism in wavelength division multiplexing, demultiplexing. Then we come to TDM, time division multiplexing. How does this work? Allow fourth machine or fourth sender to send for say t time. Then again let us make it delta t because it is very small. Allow next one to send, that is third one. Then allow second one and first one. But here the order is like this. First one is sent, then second, then third, then fourth. That is how it is arranged. So the time of allowing one to send, the two will be sent with certain delay, and that delay will be delta t. So we divide the channel with respect to the time, and multiplexing and demultiplexing will give us a single channel passing various signals or various communication. So TDM is a digital multiplexing technique for combining several low rate channels into one high rate one. This is synchronous time division multiplexing. Synchronous. Why synchronous? Why we call it as synchronous time division multiplexing? Because, as I said, these are time durations, and once we send A1, we send B1, we send C1. After that, we send A2, B2, C2. So data are taken for each line every t second. A1, B1, C1, then after A2, C2, B2, C2. So first frame will be of A1, B1, C1, as you can see here. That will be the time t divided into t by 3. So for 1/3 time, A1 will be taken, t by 2t by 3, then t by 3. So t by 3 for 3 times. That will give us t. So these all will be given t by 3 times. So first A1, B1, C1, then A2, B2, C2, A3, B3, C3 for frame 1, frame 2, frame 3. And each frame is 3 time slots. And each time slot duration is t by 3. This is synchronous because they are synchronized. You cannot have A1, then B2, then say C3, only synchronous allowed. So in synchronous TDM, the data rate of the link is n times faster and the unit duration is n times shorter, as you have just seen. So we have taken this TDM, WDM, and FDM. Now we'll concentrate next on the problems and then these spread spectrum, etc. Thank you so much.